The topic of this video is analysis of directional data, and this is covered in Chapter 6 of Wessel, and there's also a PDF on the website from Chapter 5 of Davis's textbook. That's actually a pretty thorough discussion of the topic, and I recommend you read that, download that, and read it. Now, there's two forms of data that we will talk about here. The first is truly directional data, and that's vector data, and those are measurements that have unique directions associated with them. And so the example I'm showing here are arrows of velocities measured by GPS stations from 1994 to 2003, and this is in southern Iceland. And they look to be oriented some, 110 or 120 degrees clockwise from north. So you would describe these as having azimuths of 120 degrees. And of course, these data also have magnitudes that are important to the analysis. Now, the other form of data is oriented data. And oriented data have their directions, but they have an 180-degree ambiguity in their definition. So in other words, you may define the angle in one way, but 180 degrees away from it, it has the same meaning. So there's no difference between one angle and 180 degrees apart. And the example I have here is also from Iceland. This is in the Reykjanes Peninsula. And what's plotted are individual faults, normal faults, and fissures in the Reykjanes Peninsula. And the data here would be represented, or would be the strike of these individual faults. So you can see that the faults tend to strike, something like maybe 40 degrees clockwise from north, but one could also describe those strikes as having an azimuth of 220 degrees clockwise from north. So that's an example of oriented data. So you can see how these data are represented on maps as arrows or lines. And here's another example given by Davis. Here he plots a map of arrows indicating the directions of 51 measurements of glacial striations in southern Finland. And he shows how you can represent or visualize the distribution of these directions using, for example, a polar plot. Which is the first example, in which each line represents a measurement. Now, alternatively, one could represent the data as a polar histogram. And in this situation, you divide the unit circle into a number of bins. Let's say we divide it into K bins from 0 to 360 degrees. And show pi sections, whose length is proportional to the number of observations in each bin. But there's a potential problem with this form of a polar histogram in that if the length, say the length is r, is proportional to the number of measurements, if that's the case, then the area of the pie is proportional to r squared. And so the area becomes proportional to the number of measurements squared. And that tends to exaggerate differences in the frequency distribution. You recall that for a normal histogram, when the height of an individual bar is proportional to the number of observations, the width doesn't change, right? So the area of each bar has a linear relationship to the number of measurements. But here, in a circular or a polar histogram, that's not the case. So again, the areas look too large for bins with lots of measurements. So here's a possible solution. So the first diagram shows the first case where the area is proportional to the number of measurements squared. And the solution proposed by Davis is to have r, the length, be proportional to the square root of the number of measurements. Okay, so that way the area is directly proportional to the number of measurements. And that's illustrated here. So you can see the bin with the largest number of measurements is oriented down here at, say, an azimuth of, what's that, 90 plus 40 or something, 120, 125 maybe. And it sticks out quite a bit in this first diagram, but it doesn't so much in this diagram because it's the area again that's proportional to the number of measurements. You also are able to see some of these less populated bins more clearly. So this is a more, I guess this is visually a more fair way, or this is visually a more consistent way of viewing the frequency distribution. So now let's start looking at some ways of analyzing these data. Let's imagine we have a sample of measurements. So n measured directions. So how do we compute the central or the mean direction of the sample? So the mean can be computed by just associating each measurement with a unit vector and then summing the unit vectors to produce a resultant vector. And the mean is the orientation or the direction of the resultant. So if the ith measurement is described as a unit vector, the x component is cosine of the azimuth of the angle. And I almost said azimuth. In this case, it wouldn't be azimuth. This would be the angle counterclockwise from if it's geographic from the east direction. So this is theta, and it's oriented in the x direction, plus sine theta I oriented in the y direction. Right? So the idea is to sum all of the unit vectors. So the x component of the resultant vector is simply the sum of all the cosines of each measurement. And the y component of the resultant is the sum of all the sines. So you can imagine if we have a vector that goes like that, and then another vector, so that's v1, another vector v2 that goes like that, and so forth. Then of course the resultant is the vector sum of that. And this is, I'll just call that big R with an arrow on top to denote that as a vector. And let me give myself a little more room here. So we can compute the mean angle as being the inverse tangent of the y component of the resultant divided by the x component of the resultant. And the length which we'll just call r, that's equal to the length of the vector r, and that's equal to the square root of the x component squared plus the y component squared. Okay, so theta bar is the mean of our sample, mean direction of the sample, which is the orientation or the direction of the resultant of all the unit vectors representing the measurements. And the length of r is the square root of the x sub r squared plus y sub r squared. So we have a mean, but the other aspect I'd like to point out is that the length of r is also reflective of the variance of the directions of the data set. So here's a set of examples in which the individual measurements are shown by the black lines. And in a case when all the individual measurements are closely directed, then the resultant vector, this is just the direction of the resultant vector, is in the middle of those, and it's also relatively long. And what's being plotted here is actually the normalized length, which is the total length divided by n. Okay, so these are each unit circles. The bars represent the unit vectors of each measurement, and the arrow here represents the direction of the normalized resultant vector, and its length is the magnitude of the resultant vector divided by n. And you can see here it's very close to 1. So when r is about equal to 1, then the variance of measurements is small. Now, as you can see, as the variance of the measurement starts to increase, the length of the resultant vector starts to decrease. And the way Davis has shown this is the mean direction is always the same, but for increasing variance of the individual measurements, the resultant normalized vector decreases to 0, well, close to 0. So if r bar, the normalized length of the resultant vector, is about equal to 0, then the variance is large. Right? In the n-member cases, when all the vector measurements have the same direction, and you sum the unit vectors and then normalize the resultant by the number of measurements, you'll get exactly 1. And in the extreme case is if you have measurements that alternate directions 180 degrees apart. When you sum those, of course, the resultant vector has a length of 0. Therefore, this quantity r bar is used to define what is called the circular variance. So S sub 0 squared is the circular variance, and that's 1 minus the length of the mean resultant vector, or in terms of the resultant vector, it's simply n minus the length of the non-normalized resultant vector all over n. So you can see that when r bar is 1, the circular variance is 0, and when r bar is 0, the circular variance is its maximum value of 1. So it's straightforward to calculate the mean, direction, and the variance through this resultant vector when all the measurements have a unique direction, which is true for directional data. You'll recall that oriented data, however, has 180-degree ambiguity in the direction. So let's consider how to compute these quantities with oriented data. You can imagine that, well, here's an example that Davis gives. These are elliptical depressions, ellipsoidal depressions in North Carolina, and this is an aerial photograph of them. And there was a study, numerous studies, that looked at the orientations of the uh, the long axis of these ellipsoids. And the lower diagram here shows the polar histograms of those azimuths. And you can see that some of the measurements are defined as something, what is that, about 50 degrees from north or so. But some of the measurements are also defined at 180 degrees plus that, so 230 degrees. So if you were to take all those measurements and sum the unit vectors associated with them, you may get a relatively small resultant vector, and in this case, the direction of the resultant is in kind of a funny direction. The direction not necessarily representing the mean orientation of these features. So with oriented data, we have to address the 180 degree ambiguity. And the method that Davis describes, and I'm going to refer to that as method 1, is so this works if all angles are defined as being greater than 0, and all the angles are less than 90 degrees apart. So method 1 works if these two conditions are met. And the first thing you do is double all the angles. And then for those doubled angles that are greater than 360 degrees, for those measurements, then just subtract 360 degrees. And then from that modified set, just have the angles. And when you do that, that will make all the angles between 0 and 180 degrees. So for example, we may have a measurement in this situation where the orientation is 45 degrees, and we may have another orientation that's exactly 180 degrees away from it, and that would be in this quadrant, I guess, of this unit of this circle. And of course, we want these two angles to represent the same orientation. And if we didn't do anything and sum the unit vectors, we would get a sum of 0 here, and that's not the desired solution that we seek. So this method recommends that you double all the angles, and if you double the 225 degree angle, you get 450, and then from that you would subtract 360, and that gives 90 degrees, and then you have it, and you get 45 degrees. And so that converts all the angles that are greater than 180 degrees to values within 0 and 180 degrees. And so Davis here shows the process of doing this. Here he doubles the angles and subtracts 360 from those high measurements, and he actually computes the mean of those doubled angles. And then after having the angles, he gets well, he gets this distribution right here. You can actually ignore this this quadrant right here, because he's basically, by having the angles, he gets this distribution right here, and he's just reflecting that in the other direction. I'm not sure why, but these are all the data right here. And when he computes the mean, computes the resultant, he gets this arrow here, and that's a good representation of the mean orientations of these oriented data. Now that works again. So the two requirements are all the angles are greater than 180 degrees as originally defined, and all the angles are less than 90 degrees apart. But that doesn't work if those situations are not true. So let's consider a case in which we have, I'm just going to draw a unit circle, and let's say we have a situation where we have one measured angle, say 20 degrees, and another measured angle, say at 160 degrees. If we went through this exercise, none of the angles after we doubled them would exceed 360 degrees, so we would just get the same answer back. But in reality, what we really want is to define the angles that minimize the spread in well, we want to define the angle that by either flipping it 180 degrees would minimize the difference between the orientation. So if the angles are not all positive and the spread is greater than 90 degrees, then we have to use method 2. And method 2 again is to define the angles as those that minimize the total spread of the directions. Right, so if one angle, such as this one at 160 degrees, does not minimize the spread between the two vectors, then we would subtract 180 degrees, and we would get, in this example, minus 20 degrees, and that minimizes the spread. And that method's a little more complicated because you have to consider every vector individually and flip it if needed, and that just takes a little bit of programming to arrive at the desired solution. So I'm going to conclude here, but just to quickly wrap up what we've covered, we were introduced into I introduced you to directional and oriented data. We looked at different ways of plotting these data, and then we looked at how to take a data set, compute the mean angle using the sum of unit vectors, which gives the resultant vector. And we also showed how the normalized resultant vector can be used to describe the variance, the circular variance. And last, we talked about how to address the 180-degree ambiguity associated with oriented data. So I'm going to conclude this first video here and continue in the next video.